2F is about the complement rule. And this is a very, very valuable tool to have because sometimes the event that you want to get the probability of is one that's really involved, right? Maybe it has a lot of different cases that you'd have to consider, but then the complement ends up being really simple. And then in order to get the probability of the event that you want, you could just get the probability of the complement and subtract, and you would basically have it. And so this actually comes in really, really handy because it can take a problem that's this big and make it a problem that's this big. So that's great, right? There's absolutely nothing wrong with that. And this is supposed to be about the complement rule, but because the homework kind of adds in some problems that involve independence, like you would need to use it, and even though that's really 2J, that one's specifically dedicated to independence, because it shows up here, I tried to kind of bring a little of the independence in here too. So the idea of a complement in general, because we already kind of had this for a set, right? Like when we talked about sets, we had the complement idea. It's the same thing, because you can write events like in set notation. Conventionally, I guess, like the roster notation where you list out the elements. But you can do it, right? You can write an event as a set and denote it either A with that apostrophe, which would be pronounced out loud as A prime, or, and I still write it like this. Like me personally, I would write it with the C and the superscript, like up where you would put the exponent, just like I would with the complement of a set. They are the same thing after all. But because the Newton notes and our book use the prime, I'll stick to using the prime here, just to kind of keep everything consistent. But what is the complement? Well, it's everything in the sample space that's not part of the original event. It's just everything else. So just to have something a little more concrete, if a digit is to be selected randomly, so then you've got 10 digits, right? 1 through 9 and 0. And if event A is that a prime number is selected, the only primes in there are 2, 3, 5, and 7. So that's what A is. And so then the probability of A would be 4 out of 10, since you got the 4 prime numbers. They're equally likely if you're randomly selecting a digit, right? Each digit would have a probability 1/10. So 4 out of 10, which reduces to 2/5. But then A prime, right, or A complement, that's going to be everything in the sample space that's not an A. So 2, 3, 5, and 7 are in A. Everything else is an A complement that's up here in S, right? So 0, 1, 4, 6, 8, 9. So if you had to form the complement, you would basically just look at A and go, okay, what's in the sample space that's not in A? And you would end up here. And there are 6 of them. So the probability of A complement, it's 6 out of 10, which would then reduce to 3/5. All right, so to find the probability of a complement, what you really have to do is you have to use the idea that you've got to get one of the possible outcomes, right? You've got to get something in the sample space, which would mean that when you add up the probabilities of the individual outcomes, you have to get 1, right? So to put it another way where it really kind of feels like common sense, one of the possible outcomes has to occur, right? You can't get an impossible outcome. In other words, right? Certainly not. Just by what those words mean, you can't get an impossible outcome, right? That's not even a math thing, really. And then, all right, well then, since every possible outcome, but the way that the complement is designed, it's either part of A or part of A complement, right? Because for any outcome that you can pick out in the sample space, and you can see it up here with this example, if it's not an A, it's in A complement, right? Like that's just the way A complement's defined. So that means that either A occurs or A complement occurs, right? One or the other, but not both and not neither, right? One of those has to happen. So for any event A, then the probability of A plus the probability of A complement would have to be 1 because one of those two things has got to happen. Like exactly one of them has to happen. So that equation that's there, the probability of A plus the probability of A complement equals 1, that tends to be a little bit more useful when it's solved for the probability of A complement like it is over here. So basically it's if you took this one and subtracted the probability of A from both sides, you'd end up here. And this is usually how you end up using it. Or maybe the probability of A equals 1 minus the probability of A complement, right? You could look at it that way too. That's the same idea, just from the other perspective, right? It's glass half full versus glass half empty. But that is typically how you use it. And the time to really kind of deploy this maneuver is if one probability is really complicated looking, but the one for the complement is really simple. Then you go, you know what? I'm going to get the probability of the complement, then I'm going to subtract from 1, and then I'm going to be done with this, instead of having this huge, long, involved thing. So, let's see. This first one doesn't really come off that way, admittedly, but they'll get there pretty quick. But there are questions that kind of look like this on the homework. I thought this was a good starting point. So when playing Powerball, the possibilities for the red ball, also known as the Powerball, are 1 through 26. So during a Powerball draw, what's the probability that the randomly selected red ball is not between 9 and 23 inclusive? So I know you could just count this and do it directly, right? You could just go, well, it's 1 through 8 and 24 through 26. That's 8 plus 3, that's 11. Fine, it's 11 out of 26. That is correct. But because this is the section about complements, we're going to do it with a complement. So we're going to say, what if event A is that the red ball is between 9 and 23 inclusive? Then what A is going to be is, it would be, I guess if you were going to use the roster method, 9, 10, 11, and so forth, up to 23. And if you count those, it ends up being 23 minus 8, which is 15. So I'll just say A consists of 15 outcomes, and there are 26 possible outcomes for the red ball, right? So the probability of A would then be 15 out of 26. All right, but then A prime, or A complement, that's going to be that the red ball is not between 9 and 23 inclusive. So A complement is actually a thing that we're trying to get here. And I guess I can kind of section this off, because now we're finally getting to it. But then the probability of A complement would be 1 minus the probability of A, right? Because whatever red ball comes up, it's either between 9 and 23 inclusive or it's not, right? Those are your only two options there, if that's how you're kind of looking at things here. All right, so we already know this probability. It's 15 out of 26. So we can say, well, this is 1 minus 15 out of 26. So I guess I can put the math part in here, even though I don't know that you really need to do this step. You can probably just jump right to the 11 out of 26. But if you want to get the common denominator, then yeah, and then this is what it would look like, right? Multiply 1 by 26 over 26. You're ultimately going to get 11 over 26 here. Or as a decimal, I think it's about 0.423. But I'm just going to, in my brain, that fraction feels like that's the answer. But if it said give the decimal, then I guess give the decimal. All right, so that's the idea. And I know here it doesn't look like you're saving any time, because you could say, well, you have that block from 9 to 23. There's 8 before, there are 3 after, that's 11. You know, why aren't we just doing that? Okay, well, we'll get into some ones starting right now where it will be faster if you use the complement. So the probabilities that an automobile mechanic will service 3, 4, 5, 6, 7, or 8 or more cars on any given workday are respectively right there. So the probability of servicing 3 is 0.12, probability of servicing 4 is 0.19, and so forth. Then what's the probability that he will service at least 4 cars on his next day of work? Okay, so we want the probability of at least 4, right? Or to make this a little bit more explicit with what we're about to do, at least 4 is the same thing as this, the probability of 4 or more, right? And we could do it that way, right? You'd have to add up a bunch of individual probabilities, but you could do it because you could say, all right, well, what satisfies that? 4, 5, 6, 7, 8 or more. But what about the complement? The complement of 4 or more is less than 4. There's only one possible value that's going to satisfy that, the 3. So we can do this using the complement and say this would be equal to 1 minus the probability that he services less than 4. But really, that's just going to be 1 minus the probability of 3. So this is 1 minus 0.12, which is 0.88. And if anything, it's a little bit less math doing it this way. Right? 1 minus 0.12 should work out to be the same as 0.19 plus 0.28 plus 0.24 plus 0.2 plus 0.07. Right? So here you do save some work, right? You just have to go, all right, well, the only one that doesn't satisfy this is the 3. We have its probability, just subtract that from 1 and we're done. Right? That feels a lot easier. And this is the kind of thing where if you see you can use the complement, it makes life a lot simpler. At least when you're trying to do the problem, it makes life a lot simpler. All right, number 3. This is another one where using the complement will make things shorter. So if 2 6-sided dice are rolled, we want to find the probability that the sum is in single digits. All right, well, we've had this before, the idea of rolling 2 6-sided dice. You have 36 possible outcomes, right? If you differentiate between the first die and the second die, because you have 6 outcomes on the first die, 6 on the second, right? So your sample space is going to have 36 ordered pairs in it, right? So I guess I can put that in here. So I'll just say the sample space consists of 36 ordered pairs, right? That's what it looked like when we had this before, so that's what it looks like now. And trying to figure out all the single-digit sums, because you go, well, the lowest would be 2, right? If you have a 1 on the first die, 1 on the second die, you get a 2. But you could get a 3, you could get a 4, 5, 6, 7, 8, 9, and then you start getting into, like, there are a whole bunch of different ways you can get, like, 6 and 7 and 8, right? So it might take a while to put this together. But what if instead of looking for how many different ways we would get the sum in single digits, what if we looked at how we would get one that's not? And the only option would be double digits, right? So at least for what we're doing right now, that's the only real option. So the sum in double digits. So here we're effectively using the complement, right? We're using the part that we're not asked about. We're using the opposite, right? And I guess we can just start at the top, right? You could get a 12 if you had a 6 and another 6, right? So we could have that ordered pair. There are a couple of ways you could get an 11, because you could have a 5 on the first and a 6 on the second, or the other way around, 6 on the first, 5 on the second. And then for 10, well, you could have 2 5s. That would give you a 10. And you could have a 4 and a 6, or you could have a 6 and a 4. And that's it, right? Because then that's everything for 10. The next one down is 9. That's in single digits. So the probability that you get a sum in double digits, since all of the ordered pairs are equally likely, we have 6 of them here, and there are 36 ordered pairs in the sample space, so 6 over 36, that's 1/6. All right, well, this is where we're going to use the complement rule. We didn't really want the probability of a sum in double digits. We want the probability that the sum's in single digits. All right, so the probability that you get a sum in single digits, it would be 1 minus the probability of getting a sum in double digits, which means it would be 1 minus 1/6, which would be 5/6. And that's the answer. And that's way shorter, right? I mean, if you try to do this one directly instead of using the complement, you got a lot of stuff to list out, right? Because you got the one way to get a 2 as a sum, 2 ways to get 3, 3 ways to get 4, 4 ways to get 5, 5 ways to get 6, 6 ways to get 7, 5 ways to get 8, 4 ways to get 9, right? That's a long list. And you don't need to make that long list when you can just use the complement and you'll get something that's significantly shorter. All right, so I said there was independence that shows up here, so I wanted to kind of bring in how independence works. So two events are independent basically if they don't affect the probability of the other event. Like whether or not one event happens doesn't affect the probability of the other one. So like it says here, independent if the probability of A is the same whether event B has or has not occurred, and the probability of B is the same whether event A has or has not occurred. And this next sentence without any symbolism, this is the way that I really think about it. Like just, that's the definition that's kind of just lodged in my brain. So two events are independent if the probability of one event has no effect on the probability of the other. That's the way that I think about it. And that would go in both directions, right? Like for both events. And here's the important thing, right? Like this is the part that you actually use right here. That if events A and B are independent, then the probability that they both happen, so A and B, it's just the product of the individual probabilities. So it's the probability of A times the probability of B. And the way these show up, at least in this particular section, the events tend to be repetitions of the same experiment. So like rolling a die successively, like 4 times in a row, or repeatedly drawing cards from a deck, like it says right here. I think the examples in the Newton notes, there are a couple about repeatedly flipping a coin, and then there's the birthday problem, which actually no, that's in the other section. Never mind. And that one, if you try to do it that way, it's extraordinarily long. You want to do it the way it shows up in 2e. I shouldn't be filming all these one after another. Let's see. So example number 4. So this is one where it's repeatedly drawing a card. So one card's drawn randomly from a stack of cards. Then it's put back in the deck, presumably shuffled, and a second card is randomly drawn. So then what's the probability that a queen is drawn both times? So I guess there are 52 cards in a standard deck, right? And that's what this is supposed to be, right? It's supposed to be a standard deck. So I guess we've got that piece of information, right? There are 52 cards total. And then how many queens are there, right? We kind of need that. Well, there's 1 in each suit, and there are 4 suits, so therefore 4 queens, right? So I guess if you're not used to playing cards, that's how many there are, right? So you got the 4 suits. Each suit is going to have, right, an ace, a king, a queen, a jack, a 10, 9, 8, 7, 6, 5, 4, 3, 2. So 1 queen in each suit. And so then that means that there are going to be 4 queens total. All right. But then we have 2 draws of a card, right? So the probability of a queen on the first draw, if you just look at that one by itself, you'd say, well, there are 4 queens, there are 52 total cards, there should be 4 over 52, which would then reduce to 1 over 13, right? But then the probability of a queen on the second draw should be the same, right? Because the first card's replaced, you know, you have a deck of 52 cards again. You're randomly selecting again. This is also going to be 1/13. But what happens on that first draw and what happens on the second draw, they don't have anything to do with each other, right? And since they're successive, the only way that they could be dependent is if what happened on the second draw was somehow affected by what happened on the first. And that's not going to take place here. It would if you didn't replace the card. But we're not going to worry about that for now. So what we're going to end up with, since what card is pulled on draw number 1 is going to be independent from what's pulled on draw number 2. So I guess then what we can do, and this will be kind of long when I write this, at least left to right I think it might be. So the probability of a queen on both draws would be equal to the probability of a queen on the first draw times the probability of a queen on the second draw. There, barely got it in. All right, so this is where you get to use the independence. It's right here, right? That you can say, okay, we want queen on first draw and queen on second draw, but we can write that as the product of the individual probabilities. And this will be 1/13 times 1/13, or 1/13 squared, if you want to write it like that. Either way, it's 1/169. And there's the answer. And this is the kind of thing, like the ones that involve independence in this section, this is the kind of thing that you end up with, where it ends up being the same number multiplied together. More than twice sometimes too. Like if you were drawing 3 cards, then you'd have 3 1/13ths multiplied together. If you were drawing 8 cards, you'd have 8 of them multiplied together. And that would be a huge denominator. But anyway, the next thing is, so suppose 4 fair dice are tossed. So I guess instead of the same one over and over, just throwing 4 of them all at once. So then what's the probability of rolling all 3s? Okay, this one, so this is 3 on the first and 3 on the second and 3 on the third and 3 on the fourth, but those 4 dice are going to be independent of each other, so we can turn this into multiplying individual probabilities together. So for part A, the probability of all 3s, it would be the probability of 3 on the first die times the probability of a 3 on the second die. And I'm going to have to kind of shorten this just to fit everything on the page. There would be probably 3 on third die where I have that, the ellipsis, the 3 dots, times the probability of the 3 on the fourth die. Fits on the page barely. Okay. But then on any individual die, the probability of rolling a 3 is 1/6, right? So you'd have 1/6 times 1/6 times 1/6 times 1/6, right? 4 of them, since there are 4 dice. And so then this ends up being 1/6 to the fourth. 1 to the fourth is 1. 6 to the fourth is 36 squared, which I think is 1296. Yeah, okay. So it's kind of rare, right? 1 in 1296, that's not very often. And that's one where you don't have to use the complement. So this one's just for independence. B is one where you're going to want the complement. Because the probability of rolling at least 1 3, if you do that one directly, it's really, really long. Because then you'd have to get the probability of rolling exactly 1, plus the probability of rolling exactly 2, plus the probability of rolling exactly 3. I guess you don't need the probability of rolling exactly 4, because that's what we just got, right? That's part A. But you'd have to add all those together, and not to mention, you have to worry about ordering. So then you got to also start using combinations to take care of all the different possible orderings. If you try to do B directly, it's hard and it's long. And we can avoid both of those. And we can have something that's short and at least relatively simple. So that's what we're going to do. So what we're going to do with B is we want the probability of at least 1, 3. But if you use the complement of at least 1 would be getting less than 1, so that would be getting 0. So that would be 1 minus the probability of no 3s. All right. We can figure out the probability of no 3s. I guess I'll do this indented a little bit. So the probability of no 3s, it would be the probability of getting not a 3 on the first die times the probability of getting not a 3 on the second times the probability of not a 3 on the third times the probability of not a 3 on the fourth die. Okay, so what's the probability of not getting a 3 on one individual roll of 1 die? Well, it's 5 out of 6, right? Because the probability of getting a 3 was 1 out of 6. 5 out of 6 is everything else, right? It's 1, 2, 4, 5, 6. So this is going to be 5 over 6 times 5 over 6 times 5 over 6 times 5 over 6. So we get a 5/6 for getting something other than 3 on each of the 4 dice. And the dice are all independent of each other. So to get not a 3 on the first, and not a 3 on the second, and not a 3 on the third, and not a 3 on the fourth, we can get there by multiplying. And this is, well, it's 5 to the 4th over 6 to the 4th, or 5/6 to the 4th. But what you're going to end up with, so 5 to the 4th is 625, and then 6 to the 4th, we already had it. So now I know what it is. It's 1296. All right. So then we can kind of follow this, and now we can actually do what we want. So the probability of at least 1, 3, it's going to be 1 minus 625 over 1296. And let's see, so that would be 1296 over 1296 minus 625 over 1296. And that should then be 671. 671 over 1296. Or, let's see, 0.518 as a decimal. So there we go. And this one, it's so much easier with the complement. If you don't use the complement here, it's a ton of work. You would actually have to use something called the binomial distribution to get it right, which I don't think we're even going to cover. But it involves combinations, and we talked about them. It's doable, but it's so much longer. It's probably, it's at least 10 times as long. So this is where having the complement helps out so much. So, right, 10 times as long, that does not sound ideal. So we should avoid that scenario. All right, then number 6, 5 cards drawn successively from an ordinary deck of 52 cards and with replacement. So draw the card, put it back in, and then drawn randomly. So what's the probability of drawing at least one face card? Well, then you think there are 3 face cards in every suit, right? King, Queen, Jack. And there are 4 suits, so there should be 12 face cards, right? So I guess I'll say 3 faces, 4 suits. That means there are 12 face cards in a standard deck. All right. So then what we would need or at least what I think is going to help here, the probability of drawing a face card on a single draw. Right? We can figure that out because we know that there are 12 face cards and there are 52 cards in the deck, so it's 12 over 52, right? So the probability of a face card on a single draw it would be 12 over 52, and both of those numbers are divisible by 4. This reduces to 3 out of 13. Okay, well, what we want is with the 5 draws, we want the probability of at least one face card. All right, so the probability of at least one face card in 5. Uh-oh. I lost the ability to draw. Turn it off, turn it back on. Oh, it worked. This is another at least one. And whenever you see at least one is the thing that you want a probability of, that is where you really want the complement, I think. And then you can just subtract from 1. For me, I look at least 1 as being a big red flag. Like, at least 1 is probably a bunch of work, and just getting the probability of 0 occurrences is going to be a lot less. And that is what we're going to do here. So, at least 1, the complement of that is none. And that's going to be way easier. So, 1 minus the probability of no face cards. Right? In 5 draws. I don't have enough room to write it left to right. Okay, so then we should figure that out, right? The probability of no face cards in 5 draws. All right, well, if on any individual draw, the probability of getting a face card is 3 out of 13, then the probability of getting something else is 10 out of 13, right? So we want 5 consecutive draws, no face card. So 10 out of 13 for the first draw, because we don't want a face card there, and then a 10 out of 13 for the second, and then for the third, and for the fourth, and for the fifth. And conventionally, you could just write that as 10/13 to the 5th power. And what that ends up being, I actually have it written down. The numerator I know, that's going to be 100,000, right? 1 and then 5 zeros. And then the denominator, this one I don't know, 371,293. That's what you get when you raise 13 to the 5th power. And so then this ends up being, and this one would be one where if the numbers were going to get this big, the homework would just say do it as a decimal. Because then you could simplify this part, which is about 269, and then you could get the thing that you were supposed to get just by subtracting 0.269 from 1, which is a lot easier than dealing with this fraction with these giant numbers on it. So that's what we're going to do. So the probability of at least one face card in 5 draws, it's going to be 1 minus 0.269, which is 731. Barely fit it on the page, but I got there. Okay, so at least one face card. If I scroll up to number 5, rolling at least 1 3. So at least 1, if you see that, you want to be thinking complement. And then, and it's probably going to be one where you have to use independence, right? Because there are repetitions in these, right? Number 5, the thing that's being repeated, I guess they're happening simultaneously, but it's rolling a die, right? It's happening 4 times. There are 4 replications of it, of rolling 1 die, happening simultaneously. And number 6 is in succession, but there are 5 replications of drawing a card randomly out of a deck. Then how about number 7? This one is a little bit different, although you still have to use independence, because this is one where it's not the exact same thing repeating. I guess you could view it as it's the same task, because if a tennis player is randomly going to select 1 ball out of each of 3 bags, I guess they are repeating the task of reach into the bag and pull a ball out, right? But the 3 bags don't have the same numbers of yellow and orange balls in them. So this one's a little bit different, but there are questions in the homework like this. So, all right, we got 3 bags of tennis balls, each containing some yellow tennis balls, some orange tennis balls. So the first bag has got 7 yellow, 2 orange, second's got 4 and 3, third's got 4 and 1. And suppose a player randomly selects 1 tennis ball from each bag. Then what's the probability they select at least 1 orange ball? Hey, look. At least 1. There's the red flag. Right, there's the red flag that we should be using the complement, because this one directly is extremely long. It's longer than the other ones, because the probability of getting an orange ball out of any individual bag, like, it shifts from one bag to another. That makes it way longer. So yes, complement here, no question. If you do it the long way, it's probably 20 times as long as using the complement. So we're going to stay away from that, and we're going to get the probability of at least 1 orange ball by figuring out the probability of no orange balls and subtracting that from 1. Okay, so then we're going to have to look at these bags individually, because they have different numbers of yellow and orange balls in there. So the probabilities for the bags are going to shift around. It's not going to be the same number for every bag. So, all right, well then for the first bag, then I guess the probability of not orange, that feels really weird to say, because it seems like you would just say probability of yellow. But I want to keep this thematically unified here. So not orange and yellow here, I guess, are kind of the same thing. But for not orange, there are 7 yellow out of 9 total. Right? It's 9 total from 7 plus 2. Then for the second bag, we can do the same thing. The probability of not orange. Let's see, there are 4 yellow, 7 total, so 4 out of 7. And then for the third bag, the probability of not orange, there are 4 yellow, so 4 not orange, out of 5 total, so 4/5. Okay, and then the bags are independent. Right? Like, what happens when the player pulls a ball out of the first bag? It has no effect on the second bag, has no effect on the third bag. Right? So the bags are, that's a terrible looking S. Bags, there we go, are independent. And that would mean that the probability of no orange balls is going to be equal to 7/9 times 4/7 times 4/5, right? So it's the probability of not an orange ball from the first bag times the probability of not an orange ball from the second times the probability of not an orange ball from the third. Oh, look, we got to multiply all this out, but there's actually stuff that we can cancel. Nice. So then this ends up being 16/45, which is about 0.356. So then if I scroll down slightly just so I can actually write a little bit more, the probability of at least, I'm missing a letter, least, there we go, one orange ball is going to be 1 minus the probability of no orange balls, so 1 minus 0.356, which would be 0.644. And that's the answer. So this is another one where you use independence because we used it right here. But it's not like just repetitions of the same fraction being multiplied together. Because if we go back up here, that's what number 6 is, right? All these 10/13ths. That's what number 5 is, all these 5/6. You want to keep going. That's what this one is up here, number 4. So this does come up in the homework for this section. It's a little bit different just because those individual probabilities aren't all the same, but it's still possible to reason your way through it, right? If you think, okay, we're going to get the probability of no orange balls, so we need one that's not orange on the first pull out of the first bag. We need one that's not orange on the second pull out of the second bag, and we need one that's not orange on the third pull out of the third bag, right? So we could kind of just use this stuff up here and figure those individual probabilities out. And then independence still works, so we can multiply those together. And then once we have the probability of no orange balls, then we could just use the complement to get the thing that we were actually trying to find. But the biggest thing, I think, especially because these are tougher, like the first couple at the beginning, those I don't really think are that bad. But the ones where you have to use independence, they can get a little bit more involved. But one of the biggest things is whenever you see at least once, you probably want to use the complement. That's a lot easier to remember now because when you're doing the homework for the complement section, you think, well, yeah, I should be using the complement a lot, right? I mean, sure. But like as far as the test goes, when you see a probability of at least one, that's where you want to see that red flag, right? You want the antenna to go up. So that's what you want to look for. When you see at least one, you're probably going to want the complement.